Thank you very much. It's a great honor for me to participate to this very important conference. Let me say that, of course, I join the statement of Jos van der Walle and my pre-presentations. I know Tamás for more than 30 years. I met him 30 years ago, and he was always a deep friend, an ideal researcher, a pioneer in many directions, which shape already still today actual research in nonlinear circuit theory, nonlinear circuit dynamics, in future computing systems. And I would like to, let's say, connect actual research to the pioneering work of Tamás Roska. We all know that Tamás has been pioneering as a cellular neural or cellular nonlinear networks. I copied out of one, let's say, overview paper, cellular wave computers for brain-like spatial temporal sensory computing. By the way, a paper which is still under very large distribution. Many researchers are reading this paper and related papers where Tamás summarized the concept of a cellular neural network, the principle, and the attractivity. We have in Dresden different running projects, especially people are working on 6G communication systems. There is a huge project together with the Technical University of Munich, a project with more than 100 million euros is, let's say, the funding, let's say, grant for this project. And here, the problem, how can you generate intelligent system, autonomous system that are doing sensing and processing autonomously on the device is a very, very hot topic. This shows that the pioneering work of Tamás still influences actual research. And let me give you an example. So we are on a good way to build brain implants to help epilepsy patients. We have done a laser welding control system which runs with 10,000 frames per second and reproduces very accurately features and can control laser beam technology. This is in industrial application. And I have studied with Tamás. I remember the time when I was in Budapest in 1993, and I had a very nice discussion with Tamás. And we are envision the usage of dynamics, of complexity in spatiotemporal systems. And Tamás has spent a lot of attention to, let's say, the modeling of partial differential equations. And finally, to make the long story short, the outcome was that we can control systems that are generating complex dynamics, for example, solid tone behavior in here in one-dimensional systems, but also in two-dimensional systems. This is an example of an Korteweg-diffuse cellular neural network. By taking these results into account, we further developed a new kind of cellular neural networks that shows the work of Tamás was so important that stimulated further work. And here in this context, we consider memristors. Memristors are nanoelectronic elements that have been predicted by Leon Schur already in 1971. And meanwhile, there are many groups are working on this new kind of nanoelectronic device, which are characterized by a pinched hysteresis loop. These devices will be fabricated in 3 nanometer, 5 nanometer, but even, of course, larger sizes, but the smallest size at the moment is in this range. And they have the capability to build a new kind of storage. They can be used for the generation of implants. You can generate chaotic dynamics. You can do build up man-resistive sensors for sensing Ebola virus or coronavirus. And you can do neuromorphic computing and, of course, MEM computing. MEM computing is a new idea how to advance computational technology because you overcome the so-called von Neumann bottleneck, which von Neumann systems have the separation of the CPU, the central processor unit, and the memory system. Almost 70% of the energy goes in the data exchange. So this is not very effective. And with in-memory computing, you have to use memory for computing as well. So you have no data exchange. And there's a lot of work going on. And let me mention that cellular neural networks are part of this. So this shows that the ideas of Tamás has still a very strong influence on actual research, and new structures have been built up. For example, a memristor cellular neural network as a universal in-memory computing system. Basic idea with this memristor cellular neural networks, we see the basic circuit structure of a cellular neural network. We are going to replace the standard resistor by a memristor as it can be seen in the slide. And by doing this, we generate, I'm leaving out the mathematics, a system which has a CNN state equation and a memristor model state equation. So it's a second order equation. And the advantage of these structures is when we look on the dynamic route map of a cellular neural network. So we see on the right-hand side, the classical structure of a dynamic route map of a standard cellular neural network. And the advantage of a memristor version is that we have two curves for the depending on the state of the memristor, which can be an off state and an on state, depending on the resistivity of this device. That means the capability of a classical CNN in programming is simply doubled when we consider a memristor version of this. And these structures are now under investigation in different groups. There is a group at THW Aachen in Jülich. They are doing a hardware implementation. There is a group in the United States at Amherst, Massachusetts University of Technology. Professor Chang-Fei Cha is doing a memristor version of cellular neural networks. And this concept is so powerful that you can use it as an in-memory computing system. There are templates that are doing a recall operation. That means you have a CNN operation that are giving the memristor state at outputs, and you have a store operation that you can store inputs into memristor states. That means you have your memory directly in the cell, implemented in a cell, and you can use these kind of networks for computing, but also as memory elements. These structures have two functions. Let me leave out the next slides. These are technical details and give you a take-home message. With the pioneering work of Tamás, new kinds of structures have been developed that will overcome the bottleneck of von Neumann machines that will be included in new communication systems. They are universally in-memory computing, as it is shown here in this take-home message. They can be, they have two functions. They have act as a memory system, but also as nonlinear dynamic arrays. And finally, we have the capability with these structures to do analog computing on chips. So we have already implemented structures that are very efficiently can solve NP-hard problems. With these words, I would like to thank very deeply Tamás for his fantastic friendship, for his excellent work, and I really miss him. So I am really very thankful the time which I can spend together with Tamás. Thank you very much.